Hello everyone. Today we are going to look at two popular hash algorithms. Okay, so we're going to look at MD5 and SHA. Okay, in your syllabus says SHA 512, but we're going to look at the general structure of SHA, and of course we will also discuss SHA 512. Okay, so MD5 algorithm is a hash algorithm, and MD stands for message digest. Okay, so what exactly is this message digest? In this diagram, you can see over here that it is a hash algorithm. So the hash function calculates a unique fixed size bit string representation called a message digest. So if you have a message, you get, when you hash the message, you get as output a fixed size bit string. Okay, and the message digest can be created for any arbitrary block of information. So the size of the message does not matter. Okay. Next, you can see over here, if any given bit of the function, that is the function's input, that is if the message changes, then the output, every bit in the output has a 50% chance of changing. Okay. And the third thing is that it is computationally infeasible to have two messages or files with the same message digest value. Okay, so from all this, we can see that a message is given as input to the function, and as output, you get a hash value, which is called the message digest. Okay, depending on which MD algorithm you're taking, the size of the hash value will change. Okay, now this hash function is a one-way hash function because we saw earlier that from the message, we can get the message digest, but it should not be possible to get the message from the message digest. Okay, so it is a one-way function. It cannot be reversed. Okay, why hash? The fingerprint of messages, that is the fingerprint is the message digest. The message digest does not tell us anything about the actual message, and the reason is that there are infinitely many possible equations which can give us that same result when we input the message. Okay, that is why it is not possible to say which function has been used and which message is given as output. Now, what are the principles of a message digest? One, it should be easy to compute. The same message must give the same message digest always. It should be difficult to reverse. That's from the message digest. It should not be able to predict the message. A different message must give a different message digest. And it should be collision resistant. And birth rate, if it is not collision resistant, that is, if the particular function is not collision resistant, then birth rate paradox can be used to find the collision. Okay, so we can find a different message with the same message digest if it is not collision resistant. We've seen this earlier when we discussed hash. Okay, now a brief history about message digest algorithm. There were a series of message digest algorithms. Original message digest algorithm was called MD. Okay, then MD2 was found in 1989. It was designed for the 8-bit PC with 18 rounds, but it was found to be weak. MD3 was a failure, so it was never released. MD4 was released in 1990. This digest length was 128 bits and it had 3 rounds, but this was also found less secure. Okay, then MD5 came about in 1992. It is still used, and we are going to discuss MD5 in detail because this is your syllabus. Okay, then MD6 was released in 2008. And in this particular case, the length of the digest, message digest, can vary up to 512 bits, and rounds were possible. 512 bits and 512 rounds were possible. So we are going to discuss in detail MD5. Okay, how does MD5 work? First of all, the digest length, that is the output, is going to be 128. bits. We're going to look in detail how we get this 128 bits. So the input size has to be 512 bits, and this input is further divided into 32 4 32-bit subblocks. Sorry, 4 rounds are there, but the number of blocks are 16. So 16 total subblocks will be there in each round. Okay, then iterations per round is in each of these 4, there will be 16 rounds for each subblock, and then the chaining variable is 4 into 32. Okay, so the total of these 32 bits will be changed. So there are chained. So there will be 4 into 32, 128 chaining variables. We are going to look in detail what the chaining variables are and what the constants are and things like that. Okay, so 4 into 32, 128 chaining variables will be there, and K of T constant, where there are 64 K of T constants, and the output is 4 32-bit blocks. So 4 32-bit blocks means 128 bits. Okay. Now, what are the steps? The first step is padding. So we saw that the input size is 512 bits. So if there are 512 bits are not available, then it should be padded. Okay. Then the length must be appended to the 512 bits, and divide then the steps that we said earlier, divide the input in 500 and the total message into 512-bit blocks, initialize the chaining variables, and then do the processing. Okay, now what are the basic processes? First, copy the chaining variables, which has been initialized over here, into temporary variables, create subblocks within a block, and input to round temporary variable 16-bit subblocks, and that is the inputs to the round are temporary variable, that is this chaining variable, 16-bit subblocks, and a constant T. Okay, we're going to look at this. Now, this step, we are saying initialize the chaining variable and copy the chaining variable to the temporary variables and things like that. So what are the initial values for the chaining variable? There are 4 128-bit buffer with 4 registers is used, and they are initialized to A. The first value is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Then C is F, E, D, C, B, A, 9, 8. These 2 are easy to remember, but here you have to, like, it is the, opposite direction of B, and D is opposite direction. So if you look from back, F, E, D, C, B, A, 9, 8, and 7, 6, 5, 4, 3, 2, 1, 0 is for D. So these 4 values can be remembered easily. Okay, so initially for the first round, these are the 4 initial chaining variables. Okay, now let's look at this point, the message is going to be divided into 512-bit blocks, and it goes through this compression function because the output is 128 bits. The message digest itself is 128 bits. So how exactly the 512 bits is converted to 128 message digest? Let's look at that. First of all, we saw already that in each, there are 4 rounds in the MD5 algorithm. So these are the rounds 1, 2, 3, and 4. To this 4 rounds in each step, we have the 512-bit input is given. Okay, in this, for the same 512-bit is given as the message input. We saw that initially A, B, C, D has got the chain. The A, B, C, D are the chaining variables. F, G, H, and I are the functions. T is that is from these 512 bits. We have got the that is, if you see over here, 16 8 bits are being given over here as input. Okay, so the first 16 bytes are given in the first round, next 16 bytes in the second round, next 16 bytes in the third round, and next 16 bytes in the fourth round. So you can see 64 into 8 is equal to 512. So that's how this input is divided among the rounds. Okay, and in each round there are 16 steps that we will look at later. Okay, so x of I is, we saw earlier that the temporary variable is there. The temporary variable are the chaining variables, which is A, B, C, D. Okay, 16-bit sub-block is inputted. That is got from the 512-bit blocks. And then there is a constant value T. Okay, that constant value is what is mentioned over here as x of I, x raised to 2 of I, x raised to 3 of I, and x raised to 4 of I. Okay, and then we know already that A, B, C, D, the chaining variables are 32 bits. Okay, and that 32 bits is got from the 128 bits initial variable. And once the first 512 bits of the message is calculated, then the previous message digest can be used as the next initial variables. Okay, this 16 bits, what it is, we will be looking at in detail later. So here, the 4 rounds, the output of the previous round is given as the input of the next round. But in the end, you can see that the initial, that is the previous messages, 128 bits, is added over here with the A, B, C, D, that is the variable, which we get as output in this particular round. And that output is the next block's message digest. Okay, now there's a specialty for this addition. The addition is mod 2 raised to 32. So again, the output should be 32 bits. So when you add this, the output that you get will be brought to 32 bits by doing mod 2 raised to 32. Okay, so this is the inner working of the MD5 for 512-bit block. And this is called the compression function. Okay, now we are going to look at, after all the 512 bits, it might be a big message. That big message has been divided into 512-bit blocks, which has again been divided into sub-blocks. Okay, so now we saw already that there are, each round has got the functions f, g, h, and I. So how exactly the operations of the functions f, g, h, and I can be expressed is shown in this particular function. The input is A, B, C, D, the changing variables. And there is another function G, which is once again different for each round. So we'll be looking at it later. And this is what is being done. A is added with the output of B, C, D, G of B, C, D. Okay, and that output is added with x of k. That means in that particular round, which was the constant value, that it is going to be added with that. And that output is added with the particular byte, t of which byte we are working on, that t of I value will be given over here, will be added over here. And then there is a clear, one second, circular left shift. Okay, there is a circular left shifts, and the output of that is going to be added with B, and then the next ABC is given in this way. A will be given to the next, the output of A will be given to the next B, output of B will be given to the next C, output of C will be given to the next D, and the output of D is going to be given to the next A. So this is the function. This is straightforward, but what is G? I told you G is different for each round. Okay, so this is an 8-bit left shift, circular left shift is done over here. Okay, now this is G. Now look at G. In the first round, G is equal to B and C. So here this is B, C and D are the only inputs to G. So for each round, B and C, first round, B and C or B complement and D. Second round, B and D or C and D complement. Third round, B XOR C XOR D. And in the fourth round, C XOR B or D complement. This is the function. You should learn this. Okay, so this is the G's. Okay, so with this, we have seen how MD5 converts a 512-bit block to a 128-bit message digest. And this is a small comparison between MD3 and MD4. The number of rounds in MD3 is 3, whereas in MD4 there are, MD4 it is 3, and MD5 there are 4 rounds. The additive constant T is the additive constant T is this. In MD5, it is the same for all iterations, but we saw that in MD4, it is the same for all iterations, but we saw in MD5, it is different for all the iterations. We saw that what the process P is. See, this is the process P, and it is less random for MD4, but more random for MD5, and the security is less for MD4, but more for MD5. Okay. Next, let's look at the SHA algorithm. Again, we're going to discuss the SHA algorithm in general, but our syllabus is SHA 512. So concentrate on SHA 512. The basic steps are the same. That is why I'm discussing all 4 of them. Okay. Now, what is SHA? Again, it is a hash algorithm, but it is a secure hash algorithm, and it is used specifically for authentication. Okay, so the different types of SHA algorithm that we are going to look at is SHA 0, 1, 2, and 3. In the 2 category, we have 256, 384, and 512. Okay, so we're not going to look at all of these. We're going to look at some of them. Okay, now what exactly is the hash function and how secure is it? If you look at this, this is the SHA function, cryptographic hash function. And we see over here, different inputs are given to the same function. The first input is fox. The second input is the red fox jumps over the blue dog. The red fox, next input is the red fox jumps, only V from this previous message is changed and it becomes U, the blue dog. Everything else is the same. Only this overs V is turned to U over here. Here, there are 2 alphabets that have been changed. So it is, instead of VE, it is EV. And here, V is missing. Okay, but you can see that the output is totally different for even a small change in the message. Okay. Now, a cryptographic hash function will be able to take an arbitrary block of data and return a fixed size bit string. So the size of the block of data will not matter. The data to be encoded is called the message as earlier, and the output will be called a message digest or simply digest. Okay, the output is the hash value. Okay, and it can be used for both digital signatures and message authentication codes. What are the properties of SHA in specific? As earlier, it should be easy to compute the hash value from a message. It should not be able to generate a message from the hash value, and it should be infeasible to modify the message without changing the hash. In addition, 2 different messages, that means collision should not be there. It should be collision resistant. 2 different messages with the same hash should also be infeasible. Now, we already saw what is pre-image resistance, second pre-image resistance, and collision resistance. All these 3 properties are in hash also. So pre-image resistance is, given a particular hash value, we should not be able to find the message. So it must be one way. Okay. Second pre-image resistance means we should not be able to find a second message M2 where M1 and M2 is not the same but has the same hash value. So this is also called weak collision resistance. Okay, and then there is strong collision resistance where it should be difficult to find two different messages M1 and M2 with the same hash. Okay, if there is no collision resistance, then birthday paradox can be, or birthday attack can be used to find break the security of the hash. Now we are going to look at the SHA-1 functions. Okay, now to the function at a particular time t, okay, at a particular instance t, x, y, and z is given as input. If the t value is between 0 to 19, then the choose function is used, and the function, what it does is, it does x one second. So in SHA function, as I told you, when the t value is between 0 to 19, the choose function is used, and what the choose does is x and y, XOR x and z. Okay, if the t value is between 20 to 39, and if the t value is between 60 to 79, then the same function is used. The parity function is used. Again, input is x, y, z. It simply XORs the three values. Okay, and if the t value is between 40 to 59, then majority function is used, and the function, what it does is x and y, XOR x, y, x and z, XOR y and z. Okay, so this is these are the functions which are used for SHA-1 function. Okay, in the case of SHA-256, I just want to go back to show you, this is SHA-2. Okay, 256, 384, and 512 are SHA-2. So in essence, we are discussing SHA-1 and SHA-2. Okay, so 256, SHA-256 function has got a choose function, x, y, z. What it does is exactly the same as SHA-1. Okay, and the majority function is also the same as SHA-2. In addition, there is a summation 0 to 256, summation 1 to 256, standard deviation or variance 0 to 256, and sigma 1 to 256. And what these functions do is, for 0 to 256 summation, rotate right twice the x value, XOR rotate right 13 x value, plus rotate right 22 x value. Not plus, this is XOR. Okay, this is rotate right 13 bits, 2 bits, 22 bits. And this symbol is for XOR. Everything is being done with the input value x. Okay, in the case of 1 to 256, this is 6, 11, and 25 are the rotate right values. I mean, rotate right 6 bits, rotate right 11 bits, and rotate right 25 bits of x. Okay, in the case of sigma 0 to 256, we have rotate right 7, 18, and shift right 3. Okay, and in the case of sigma 1 to 256, we have rotate right 17, rotate right 19, and shift right 10. So these are the functions which are going to be used, which are used in SHA-256. Okay, we are going to discuss all the bits and pieces, and then we will look at the actual algorithm to get the hash value. Okay, in the case of both SHA-384 and 512, the functions are the CH and the majority functions are exactly the same, but the sigma and the summation and the sigma functions are different. So this is the only difference over here. So this is different from this particular function, these particular functions in SHA-256. Okay, now the constants that are going to be used in the case of SHA-1. For if the t value is 0 to 19, then this is the constant that will be used. 20 to t39, this is the constant that will be used. 40 to 59, this is the constant. And 60 to 79, this is the constant. Okay, in the case of SHA-256, all these constants are there. And in the case of 384 and 512, a lot more, different values are there. Okay, now we're going to look at the actual steps. There are two steps involved in the SHA hash algorithm, a pre-processing step and an actual hashing step. So we're going to look at the pre-processing. 3 steps are there. 1, padding. 2, parsing. And 3 is setting initial hash values. After these 3 things, we're going to look at each of these. After these 3 things are done, then the actual hashing is going to be done. Now, what is padding? The message M, we already saw earlier that SHA takes as input any arbitrary message. Okay, the size of the message itself does not matter. That is why we have to do padding. Okay, so the message should be padded before the hash computation begins. The purpose of this padding is to ensure that in different SHA algorithms, the size of the blocks should be different. So in the case of SHA-1 and SHA-256, 512-bit blocks are used. And in the case of 384 and 512, 1024-bit blocks are used. Okay, so depending on which algorithm we are using, accordingly, padding should be done. Now, how exactly is this padding done? This L over here is the length of the message. So length of the message plus 1 plus K must be equal to 448 mod 512. Okay, 448 mod 512. And in the case of 384 and 512, L plus 1 plus K must be equal to 896. That is 896 mod 1024. Okay, so if you look at these two values, this is just into 2. 896 is in 448 into 2. And 512 is, 1024 is 512 into 2. Okay, now, this is how the padding is done. Now, parsing. How the parsing is going to do. After a message has been padded, it must be passed into N, there will be N M-bit blocks. So we saw already SHA-1 and SHA-256 requires 512-bit blocks. So there will be N 512-bit blocks in SHA-1 and SHA-256. And in 384 and 512, there will be N 1024-bit blocks. Okay, so this is the next thing. It is divided into the different block sizes. Then the initial hash values. In the case of SHA-1, the initial hash values are 5 32-bit words. Okay, so those 5 32-bit words, H0, that is the initial value, the first initial hash value is equal to 67452301. Then the second 32-bit word is FCDAB89. And then you can see over here that just like earlier, these two values from the back is these two. Okay, so 98 BADCFE is H2 initial value, and 10325476 is the third hex value, and then the fourth hex value is C3D2E1F0. Okay. Similarly, and now I'm not going to look at each of these values. SHA-256 has got 8 32-bit words as initial values. SHA-384 also has 8, but 64-bit words in hex. And SHA-512 also has 8 64-bit words as their initial hash values. Okay, so what do we know till now? We looked at all the bits and pieces. So basics is that the hexadecimal digest 4-bit and digits is 4, hex digits is 4 bits, and the words are 32-bit and 64 bits. The operations that are done are shift right, rotate left. Okay, functions are choose, parity, majority, sigma 0, sigma 1, summation 0, summation 1, sigma 0, and sigma 1 of X. Constants, there are 80 in SHA-1, there are 80 32-bit words. So K0 to K79 are there in SHA-1. In the case of SHA-256, there are 64 32-bit words, K0 to K69. In the case of 384 and 512, there are 80, but not 32 bits, 64-bit words. So K0 to K79 for 384 and 512 is similar to SHA-1, but instead of 32 bits, 64 bits are there. And then, of course, we have the initial values. Okay, now we are going to look at the actual algorithm and how it works. SHA-1. The first step in SHA-1 is that a message schedule of 80 32-bit words is there as input. 5 working variables or initial hash bits, 32-bit hashes are there. And a hash, 5 working variables are there, and a hash value, that is this. These values, these constants. Okay, so there are 5 working variables and 5 hash value of, this is not 5, this is 4 working variables and hash value of 532 bits. The final result for SHA-1 is a 160-bit message digest. First step is pad the message. Second step is parse the message into n 512-bit blocks and then set the initial values at 0, the 5 initial values at 0. Once that is done, for every I from 1 to n, prepare the message schedule W of t, that is to check whether if the t value is between 0 to 15 or 16 to 79. And accordingly, W of t will be calculated. After W of t has been calculated, the working variables A, B, C, D, E with the I minus 1th hash value. So the previous hash value is going to be used for the initial values over here. So A is equal to the hash 0 of the previous value, hash 1 of the previous value, hash 2, hash 3, hash 4 of the previous hash value. Okay, so these are the working variables in the ith round. Okay, then for t is equal to 0 to 79, these values, t is equal to, do the equation, find the t value, E is equal to D, that is, these are the next hash values. So A, B, C, D is calculated in this way. Then compute the ith intermediate hash value. So H of I is equal to this A value plus the previous A value. Okay. H1 is B value plus the previous B value. Similarly, all the 5 values are computed. Okay, and the output will be equal to, after n rounds are completed, these 5 hash values is going to be, they are appended. Okay, so these are the 5 hash values. And we saw over here that these H values are all 32 bits. Okay, so we have 5 32 bits, which gives us a 160-bit message digest. Now, hereafter, if you have understood this algorithm, all the other algorithms is the same. The only thing different will be this calculation of W of t and the calculation of t, that is these variables. Okay, so let's look at the others now. Again, in algorithm 256, the message schedule is of 64 32-bit words, 8 working variables, hash value 8 initial hash values, and the final result is a, not earlier it was 160 bits, now it is 256 this bit message digest. This is essentially the same. The pre-processing steps are essentially the same. So if you look over here, the only difference is first we prepare the message. The calculation over here is different. For t is equal to 0 to 15 and 16 to 63, the calculation is being done. And then the initial 8 variables are calculated with these particular values. Then the next hash values, the intermediate t values, are calculated using these particular functions. And then just like previously, so the only The first step and the third step is different for each of the algorithms. Otherwise, everything else is the same. And over here, there are 8 32 bits appended. So we have 256 bits. Okay. Now we are going to look at, this is important because this is your syllabus. The message schedule is 80 64-bit words. There are 8 working variables of 64 bits and hash values of 64 bits. And the final result is 512 bits. Okay, so this was, first one was 160 bits, second one was 256 bits, and for 512, we have 512 bits. Okay, this is essentially the same. The algorithm over here, if you can see that these values is exactly the same for both 256 and 512, calculating these values. Okay, then these values are calculated, and after repeating the steps 1 through 4, a total of n times, the processing is complete, and we have 512 bits. Okay, so 64 into 8, you will get 512. Okay, now we see an example of SHA-1, and similar, you saw the algorithm already. The 512 is also similar to this SHA-1. Okay, so the message over here is a 24-bit ASCII string ABC. Okay, so there are 8. Each is a byte, and there are 3 bytes. So it is 8 into, 3 into 8, 24. So the length is 24. Okay, so the equivalent binary is going to be ABC is given over here, and the message is padded by appending 1 bit followed by 423. That first the padding is going to be done, because in SHA-1 as input, we have to give, let's look at this. See, the input is 512 bits. Okay, so padding is going to be done. Sorry. Yeah, here. So we have 2 into the 32-bit words and bit word representation. First, you pad this message to give 512 bits with zeros, and then this length to represent 24. 32-bit word is, appended to the original message. So the final padded message will consist of 1 block. So for this particular message, there will only be 1 block of 512 bits. So n over here will be equal to 1. Then the initial values are taken as we saw earlier. And for each of the 16, rounds, W is going to be calculated with the particular, that is this is the particular message. So the initial message was 61626380, and then there are zeros padded, and the length is also appended. 14 and 15 is the length, and this is the total message. Okay, message block of 512 bits. Then the following schedule shows the hex values. That is, in each of the cases, after each round, there are 79, that is 80 rounds, and ABCD values keep changing for each T. So when T is equal to 0, ABCD values is from the previous ABCD values, these values are calculated. And for each round, the ABCD values, hex values, will change. So this is done 79 times. Okay, and finally, the values which we get for H0 is going to be added with the previous value. See, the first one I will show you, 67452301, and so this is A, right? This one, see? The previous value is 42541B35. Okay, and that is added to this 67452301. So in the 0th step, the initial hash value was 67452301. After the first round, the hash value is 42541B35. So over here, the previous value and the current value is added, and that is our next hash. So in the next round, the initial hash values will be these 5 values. Okay, and in this particular case, since there is only one block, this is the final hash or SHA message digest for ABC, the string ABC. And with this, we are concluding today's lesson. Both MD5 and SHA-512 are popular hashing algorithms, which is part of our syllabus. See you again in the next class. And as usual, don't forget to like and subscribe. And don't, if you have any doubts, feel free to contact. Thank you.